back, folks, to the WP-Tonic show. It's episode 550. We've got a fantastic guest. We've got Matthew Renze with us, and he's a data scientist, a consultant, an author. He knows everything about artificial intelligence and big data. He's been very gracious to say that he'd come on the show. It's going to be a little bit different, but we're really going to delve into this world because I'm sure like you, I've been hearing about artificial intelligence and big data for the past 5 years. Literally every tech story, it has some element of big data or artificial intelligence. Before I introduce him, I like to introduce my co-host, Stephen Saunders. Stephen, would you like to quickly introduce yourself?
Yeah, my name is Stephen Sauter. I'm from zipfish.io. We specialize in making WordPress fast by optimizing both servers and the code that runs your site.
That's great. And before we go into the main part of the interview with Matthew, I'd like to talk about one of our sponsors. That's Kinsta Hosting. Kinsta Hosting is a specialized WordPress hosting company. It has been supporting WP-Tonic for a couple of years now. Why should you be interested? Well, it provides really fantastic hosting for your projects and for your client projects, especially if you've got WooCommerce or a large learning management membership website. You need quality hosting, and they're one of the better providers in the field. They only specialize in WordPress. They provide all their hosting is on the Google Cloud. They provide a customized interface, all the technical bells and whistles, plus great support. That should be interesting for you and your clients. So go over to Kinsta, have a look at their packages. I suggest that you buy one for yourself or for your clients. And the main thing is tell them that you heard about them on the WP-Tonic show. So let's go straight into the interview with Matthew. So Matthew, thank you so much for coming on the show. Like I say, you are experienced scientist and specializing in artificial intelligence and big data. So I think we just go straight into the questions because we got a limited amount of time. So I'm going to ask a really broad and semi-difficult question, but if you can just give a very quick outline, because I think the other questions we go into more detail, don't you? So what is the difference, quickly, which is a ridiculous question in a way, but hopefully you understand why I'm asking it, between human intelligence and machine learning and AI?
Well, I'll try to do it as quickly as possible, but you're right, it is a pretty big question. So we have a distinction between artificial intelligence and natural intelligence. And the main distinction is that natural intelligence is essentially organic-based intelligence, and artificial is any machine that we use in order to simulate intelligent thought, which then we have to define intelligence, which is essentially the rational agent definition is any agent that perceives its environment and chooses actions that maximize the expected likelihood of achieving a goal of some kind. And then within organic intelligence, we have human intelligence, we have animal intelligence, and we also have collective intelligence. And then within artificial intelligence, we have artificial narrow intelligence, artificial general intelligence, and then artificial super intelligence. And then machine learning is essentially just a subtype of artificial narrow intelligence that is based on math and statistics.
That's great. Before I throw it over to Stephen, where does the Turing, the British scientist Alan Turing, and he had this test where if a machine could mimic a human being, he said that was conscious, basically that machine or entity, whatever it would, you could then classify it as having almost human level consciousness. How does that fit into what you've just said?
Well, when you think about it, when we judge other human beings as being intelligent or not, we're essentially performing a Turing test. We're essentially we're making assumptions first off, and then we're asking them questions, and the responses that we get from them help us to determine whether this person's actually intelligent and rational and conscious, or whether they're just, a robot on the other end.
Yeah, there's a lot of people that think that of me, actually. There you go.
So when Alan Turing was proposing this, he wasn't saying that this is the end-all be-all criteria for determining whether a machine is conscious or not. It was essentially trying to come up with, well, what is a heuristic for us to gauge whether a machine is producing intelligent responses or not. And I think most people would say that for them, when they would believe that a machine is actually intelligent is when it can explain exactly why it's doing what it's doing in a way that appeals to human intellect. If it can do that, most people would say, yeah, it's probably conscious. And if it's not able to do that, then it's pretty clear it's most likely not conscious. But I guess conscious in the sense of metacognition, understanding its own thoughts, behaviors, and actions, and being able to explain them or articulate them in a way that is intellectually satisfying to us as human beings.
Oh, great. Over to you, Stephen.
What does that look like? Like what's an example of something that would be like intellectually satisfying to a human being? Like a computer explaining like what does that kind of tangibly feel like, I guess?
Well, to me, for example, if a machine is unable to explain why it determined that a certain type of image contains, a diagnosis of cancer, we would say that it clearly doesn't understand it. It's a function. It's mapping an input to an output and giving us an answer. But if it could articulate exactly why it believes that this is cancer versus not cancer, and human doctors listen to this explanation, they're like, yeah, no, it clearly understands that this is, cancer because of this and that. It meets all of our needs from an intellectual standpoint. I think that's what they would say is satisfying that criteria for explainability.
Interesting. So then what about neural networks then? Because the classic thing that I hear about neural networks is that it's kind of a black box. Nobody really knows what's going on. You send enough data in, you get your result out. And then how did it come up with that? Who knows?
Yeah. And right now, neural networks are largely a black box. We train them with a set of data, and then it essentially, we give it a new input, it produces an output. And in some cases, we have bits of explainable AI that we can use in order to try teasing out why, but it's not of its own volition explaining its behaviors. It's essentially, we're kind of coding the explanations in. So we're giving it an input and we're getting an output plus another output, which is kind of like a diagnostic explanation, if that makes sense.
Interesting. And as far as neural networks go, when I think of them, often I think of them in identifying things, or predicting things, in those two different areas. Maybe that's where all AI sits. But are there other questions out there besides this is a apple, or if I throw this ball, it's going to land over there? Kind of predicting, identifying. Are there other questions that people are trying to answer outside of those two primary, very basic ideas?
Yeah, so you can use neural networks for a lot of different things. So in general, there's two kinds of categories of machine learning. There's analysis and there's synthesis. And analysis is where we're taking a complex, high-dimensional set of data and reducing it down to a simplified or more abstract version. So you take an image and you produce a label that this is a cat. You take an image of a person's skin and you say, this is cancer, this is not cancer. And you can take audio and say, well, this sound is a gunshot or not. Or you could also do what we call regression. So those are classification examples. Regression would be you show it a bunch of houses and their sales prices, and then you predict a new house that it's never seen before, how much it's likely to sell for. And so classification, regression, other areas we have anomaly detection. So what data are different from the normal data? We do cluster analysis where we're looking at the similarities between types of data and putting them into clusters. We can also do things like recommendations, very common. But beyond that, and those are all analysis tasks. In the synthesis side, we're essentially generating complex, higher dimensional data from more simplified inputs. So, and most people don't even know that a lot of this stuff exists, at least in research right now. But you can type a description of, I want to a black bird that has yellow stripes and something mid-flight. And we can actually generate an image of what that description says that looks realistic. We can do it with human faces as well too. You can just describe a female with blue eyes, blonde hair, and age 23 approximately, and you can synthesize a face that matches that, or even draw sketches, and it will, from those sketch lines, it will produce a face. And even more complex stuff. We can synthesize video now too. You feed it what we call semantically labeled images, and it will produce real-time video that looks like it's an actual car driving down the street.
Man, crazy. Jonathan,
Yeah.
Back to you.
Well, where to take that? So basically going to jump the orders slightly of the predefined questions that I managed to cobble together with my limited knowledge of this subject. But when you talk about neural networks, because obviously neural networks, the way I saw them with my primitive knowledge level was that it was like throwing that you put percentages, and it's like throwing the dice, and progressively you train the artificial intelligence to go through a layer of if and yes or no's,
yep.
percentages, probability. That was what I was looking for. And because you knew the and then it would come out with an answer. I'm mumbling there. But and then you mentioned reductionism, which is a fundamental part of science. But I was wondering, game theory, did neural networks at all? I am correct in saying it's a form of mathematics, isn't it? Neural networks, and especially game theory. Was the two kind of linked together? Was neural networks developed as a way of helping get answers around game theory, or are they totally divorced, Matthew?
Well, I think there's two questions in here. We'll start with the neural networks, and then we'll go on to game theory. So first off, with neural networks, I've got to admit that there are a lot of people in academia, I think, that are using overly complex attempts to explain these to the general public.
Never.
People,
I'm so shocked.
You've got people that I think do a really good job of explaining these things to the general public because they're not trying to inundate you with mathematical terminology and stuff like that. So the most basic way I can explain what a neural network is using a metaphor from biology. So essentially the metaphor of an actual human brain. Some people will get angry with me for even using the metaphor, but I think it works well in order to conceptualize what's going on. And that's originally where neural networks came from. They were based on this kind of crude understanding of how we thought brains worked back in like the 1950s and 60s. Mm-hmm. So you think about it as a set of neurons, just like a human brain, connected with synapses. And you've got an input coming into the neuron, and then it will fire if the threshold is high enough for activation. And then it goes on to the next layer and the next layer and the next layer. And we have some where the neurons kind of go like this, and we have some where the neurons kind of go like that. And you can think of that in terms of like the analysis and the synthesis, like metaphor that we're using. And so you are essentially training a neural network to learn a mapping from an input to an output using this conceptual model of a brain. So we train it with data. We give it a bunch of examples of the inputs and a bunch of examples of the outputs. We're giving it the answer while we're training it. And then over time, it's essentially learning this function. And so that's the conceptual, biological conceptualization of it. But in the real world, we actually model all this mathematically. So mathematically, a neural network is what we call a universal function approximator. It's essentially estimating, given an input, it's providing an estimate of the output from a purely mathematical or statistical standpoint. Once again, it's just a function. It's a mapping of an input to an output. But when we're representing this brain, if you will, or this neural network mathematically, we're doing it with mathematical operations and a bunch of numbers that we store in an array, which we call a vector. So whenever you hear about feature vectors and stuff like that, that's essentially, it's just an array of numbers. So you've got number. And if we have it in 2 dimensions, we call that a matrix. And if we have that in more than 2 dimensions, we call that a tensor, which is where TensorFlow gets its name. It's just an n-dimensional array of numbers. So 3-dimensional, 4-dimensional, or many dimensions. And then we're using linear algebra in order to compute an output given an input. Linear algebra, same thing you'd get if you were a freshman or sophomore in engineering class in college. It's not super complicated math. In fact, most high school students, I think, could do linear algebra quite easily. And then we use basic calculus to train the network or train the weights of the neural network during the training process. And that's just the gradient descent and the chain rule, stuff you learn as a freshman essentially in calculus.
Yes, but Matthew, you're using words that are instilling fear into my heart. Calculus.
Oh, really? Calculus?
Yeah, but they wouldn't touch me because I've got dyslexia. So I'm very good at business math, though. I've always been good at that. And I'm very good at the concepts, as most dyslexics are. But I didn't really give them the answers that they were looking for. So that was the end of me. I'm going to go back because I put them out of order and that probably confused Stephen, but Stephen should have got used to that by now. So let's go on. So this concept of weights, which applies to the neural networks, I presume, as I was doing my research, that is a kind of measurement of the actual output, maybe. Am I right or totally wrong there?
Well, so when you're thinking about a neural network, there's essentially three kind of concepts. We've got weights, we've got biases, and we have activation functions. And so the weights you can think of as the strength of the connection between each neuron in a neural network. So the larger the number, the stronger the connection, the lower the number, typically in a negative direction, the weaker the connection, or I guess it's a reverse connection. And so the weights are essentially representing the strength between the neurons. And then each neuron has what we call an activation function, which essentially represents when the neuron's going to fire. So if there's a little bit of input, is it going to fire right away? Or if there's a lot of input, is it going to fire? And so that's kind of controlling when the neuron itself fires, and then the weights are in between these neurons. And then we've got something called a bias, which essentially just shifts this activation function either to the left or the right. You can think of it as increasing or decreasing the sensitivity of the neuron itself. And then all of these weights we're essentially just setting during the training process using a technique that we call back propagation, which I'd be happy to explain if you'd like.
Oh, that was going to be our next question. So I think we leave that to our break, and we come back with that. Actually, sure. Hopefully we haven't totally lost you, audience, but I think it's been an interesting discussion. Keep with us. I'm sure you're going to be enlightened. We'll be back in a few moments, folks. We're coming back. We've had a feast of artificial intelligence, and what is it, and what are some of its key parts? Hopefully we haven't totally lost you, audience. I think not. I know you are a smart and intelligent audience, and you know better, you've kept with this better than me, and I'm sure Stephen totally understands as well. I'm struggling, and I wrote up the questions, but Matthew is going at a pace, which is great. So Matthew, we're gonna come back. We were talking about weights, and then a related question in our list is back propagation. What does that mean, Matthew?
So back propagation is a technique that we use to train a neural network. And I'm guessing most people aren't familiar with neuroscience, but it's equivalent to what we call the credit assignment problem in neuroscience. How do you assign a value to each neuron for its participation in choosing a correct answer? So if you've got a bunch of neurons and you make a correct answer, you need to go back and tell each neuron, hey, you did a good job when you fired or not fired in order to produce the right answer. So, but we have to do this mathematically because, we don't have organic brains inside of computers. So once again, we go right back to, we're talking freshman calculus. It's not very complicated math at all. And we use something called the chain rule in order to calculate the derivative of each neuron, which once again is basically just saying, how much credit should I give to this neuron for its contribution to the answer that it gave? And then gradually, we're just increasing or we're decreasing the weight of each of these neurons or synapses in between the neurons using this gradient descent process, essentially just moving it slightly down this way or moving it slightly up this way because it's doing a good job or a bad job answering the question. Essentially, we're providing it tiny rewards or punishments for each neuron, whether it's giving us a right or a wrong answer. And then essentially these small nudges to the weights are giving us better answers every time we punish it or reward it for a correct or a wrong answer.
That's great. Over to you, Stephen.
So I guess just to I'm just trying to build a picture of this in my head. Let's say I'm a Tesla. I'm trying to identify if something is a human because I need to know if something is a human. So that'll be our use case. So I'm trying to build a neural network that will be I guess an image identification of this is a human, this is a trash can. or not a human, I guess is like the question. So if I'm going to approach this problem, I have all this data set that says these are all humans. I feed it into my neural network, and then it processes all of that, and it knows it's all humans. So like good rewards or whatever, like going through that back chain, so that any neural network that fired when it said it was a human is a positive thing. If it didn't fire, that's also a positive thing. So those get more weights, or maybe. But then let's say I do then like the opposite, like a trash can, just to test it. And if trash cans are coming out of humans, that means I need to keep training it, I guess, right? Is that like a proper way of thinking through this?
Yeah. So yeah, every time you're running the training algorithm, it will get progressively better at detecting a human versus a trash can. And so then the more times you run it, it'll taper out, and you won't get any better as you continue to feed it more information or run it additional times or iterations. And then once you've hit that kind of threshold, that's essentially as good as that network's going to perform without doing some other kind of techniques. We can do some other things outside of that training process to make it work better. But yeah, conceptually, like that's exactly what we're doing. We feed it a picture of a human. If it guesses human, we give it a thumbs up, and that assigns the credit back through the network. If it said trash can when it was a human, then we give it a thumbs down, and that gives a negative credit back through the network. And then we feed it a trash can, and if it predicts trash can, we give it a thumbs up. And if it predicts not trash can, we give it a thumbs down. And over time, it's going to progressively get better at doing this until we've essentially maxed out the accuracy or the performance of that neural network.
And so if I'm a developer, do I just like take this, I don't know, let's say it's like some open source neural network thing that's been developed out there, and I kind of just tweak the weights or whatever? Or am I actually going in and trying to decide like these neural networks are supposed to identify these kind of pixels and should have this kind of weight? Like how in depth does like a neural network developer get into actually manipulating the neural networks, or is it more about manipulating the data sets and the thumbs up and thumbs down?
So this is a great question. And this is one of the things that I think is largely misunderstood in the developer community right now. I'm going to try breaking this into 3 different groups. We've got pre-trained models, which are essentially off-the-shelf solutions that are ready to go. A developer using one of these pre-trained models, like Microsoft has their cognitive services. We've got Google's cloud AI services and Amazon's AI services. These are off the shelf, ready to go. You just give it an input, it's going to give you an output. You don't have to do any training. You don't need to know anything about math or statistics or neural networks. You just start using it. Then we have we'll go to the other side. Then we've also got like completely custom neural networks where you're going to need a data scientist. You're going to need a bunch of data. You're going to need training algorithms and a whole bunch of compute power in order to train a model from scratch. We've got some tools that we're building like AutoML or automated machine learning, which are making this a lot easier and not requiring as many, as much knowledge or resources in order to make it happen. But, and we can talk about that too. But then in the middle, we've got something that we call transfer learning, where we take a pre-trained model that was designed to do one specific task. If this detects humans or this detects cats, and then we slightly tweak it through this process called transfer learning to have it do a slightly different task. So, well, it was designed to detect people, but we needed to detect our company's logo instead. So it's already been trained. All the hard work's been done. So all we need to do is give it a couple of examples of our company's logo, and then it will essentially adapt what it's already learned to just that new task. And that is actually relatively easy. I mean, there's the drag and drop services online to do transfer learning right now. So depending upon what type of problem you're solving in each of these 3 categories, you either need to know nothing about, machine learning, neural networks, and that stuff, or you need to know a whole bunch about it, or you just need to know enough in between to get by. But it all depends upon what you're trying to solve. And there's tools in each of these 3 categories now for developers.
Interesting. So the idea is that if somebody has figured this out fairly easy to do, kind of tweak it to what you need. If you're more on the bleeding edge of things and are trying to develop new systems, that's where like you really got to roll up your sleeves and have like a data scientist on your team and all of these other people that know exactly what's happening and how it's going on. It's not something that you could just go hire a developer from Upwork or whatever and be like, hey, do this for me.
Yeah, and it's exactly correct. It really depends upon what you're trying to do. And this is why I always recommend just start by doing a search for existing solutions to this problem. Oftentimes someone's already solved it for you, has solved a very similar problem which you can transfer the learning from, or nobody's even attempted this and you're pretty much on your own. And that's when you need a data scientist and a data engineer, a machine learning engineer.
Okay, interesting. Jonathan, I'll kick it back to you.
Right, so Matthew, earlier on in the first half of the show, you said that we don't fully understand the mathematics. So is it a similar, when it comes to these neural networks, is it a similar situation to quantum physics, that the mathematics that utilize in quantum physics works and we get outcomes that help us build the modern world? But when we try and apply quantum physics to the larger world of gravity, what came from Einstein with relativity doesn't really play well with. Is it that situation? So outside its field, the actual mathematics, or is it we really just don't understand the mathematics completely that is utilized to model these neural networks?
Well, I think I understand the comparative metaphor you're using, and I think it's interesting.
You're doing well. Most people can don't.
I don't know that it's a good mapping for the relationship to what we currently know about neural networks. So I think the thing we have to understand is that the mathematics to execute a neural network and to train a neural network we understand really well. And as I've said, it's literally the type of math.
That's why I was getting confused, because you were
okay.
you were hinting through the rest of the questions but at the beginning you were suggesting that we didn't fully understand the mathematics. That's what.
Yeah.
So thank you. I think the quantum mechanic bit I was just trying to make out. That was really intelligent, actually. There we go.
Oh no, and actually I do like the comparison, and I could speculate on how they are related, but I know just enough about quantum physics right now to be dangerous, and I would probably say something wrong, but I am studying quantum computing in order to better understand it, so that someday I'll be able to come on the show and talk to you about quantum computers. But so back to what we do know and what we don't know. So execution and training of the neural network, we understand pretty well, but we don't have a complete theory of why neural networks work the way they work. So sometimes like a neural network will work really good for this task A, and we try to get it to do task B that seems like it should work, and it just completely fails. And we don't understand why yet. We have guesses as to it, but we don't have like a mathematical theory for why it works or doesn't work. But experts are currently working towards a kind of a unified or general theory of neural networks. And I'm guessing we'll probably be there someday. And we also don't fully understand how best to implement them, but we're learning new techniques every day. In fact, every week I'm reading about a new technique someone tried that did something impressive. We've now got automated machine learning. Transformers are blowing up right now in terms of what we're discovering they can do. We have modular neural networks, spiking neural networks, a whole slew of different techniques that are eventually going to lead us to solve problems that we can't currently solve with them. And things like reinforcement learning too. And we often can't explain why neural networks are doing what they're doing from a purely, we can explain mathematically. I can show you the calculations it made to get to the decision. But in terms of an explanation that an average human being would understand, we're still quite a ways away in many domains about that. But we're getting better with explainable AI and transparent AI systems that help us to understand why neural networks are doing what they do. But what I generally recommend is always use the simplest tool for the job. Essentially, if you can get away with using just like a decision tree classifier, which is a really basic form of machine learning, like ridiculously simple. It's just a tree of decisions that it's making. Use that if it's solving the problem. Don't build a deep neural network just to squeeze out another 0.5% of accuracy. Because like if you have to try explaining to a judge why your credit approval algorithm rejected this person, you can show him the decision tree and he's going to be like, oh yeah, I clearly understand why you approved or rejected this person. But if you show him a bunch of linear algebra and calculus, he's going to have no idea, what you're talking about. So simplest tool to solve the problem.
Yeah, there we go. I think we're going to wrap up the podcast part of the show. 30 minutes roughly goes really quick. I did warn Matthew, and I think I kept my waffling down to a certain degree, listeners and viewers. Hopefully you enjoyed this interview. It's a little bit outside our normal realm. If you do, just give us some feedback, and I'll try and get some other people slightly outside the normal realm of WordPress plugins, business and development. So Matthew's is agreed to stay on for another 15 minutes, which you can see in our bonus content. So keep with us. I think it's been a fascinating discussion. So Matthew, what's the best way for people to find out more about you, your ideas, and maybe, you know, you give some other insights into this fascinating world of which we've been discussing?
So everything that I do, I try putting on my website, which is matthewrenze.com, including all of the places you can find me on the internet will be linked there, and all of my online courses. So essentially, the best way to describe my job right now as a data science consultant with a focus on AI and machine learning is that I'm trying to help software developers and IT professionals understand data science, machine learning, and AI without having to go back to college to understand what they need to know in order to start leveraging these tools today. So I'm doing my absolute best to try explaining things as simply as possible using metaphors that I think everyone can understand and trying to strip away all of the complex math out of it, because, you know, there's a place for that in academia. And if you want to go, you know, back to college in order to get a master's degree in AI, absolutely, you will need to know linear algebra, calculus, like multivariate calculus, and even more complex math than that even. But for the average software developer, because of how we've got these tools prepackaged and stuff, I don't think they need that level of knowledge in order to start using this stuff. So yeah, check out my website, matthewrenze.com.
Oh, that's great. And Stephen, what's the best way for people to learn more about you and what you're up to?
Head over to zipfish.io, run a speed test, and see how we can make your website faster.
And before we wrap up the show, folks, I just want to remind you that I'm doing a webinar. It's the second Friday of December. I think that's the 11th of December at 10:30 a.m. Pacific Standard Time. It's going to be me and Spencer Forum again, our first webinar in a series, which was last month, was a well, still this month actually, was a great success. Got a lot of positive feedback. This upcoming webinar, like I say, in December, is going to be roughly around the same thing, but with additional information. We're going to be showing you actively how you can integrate a WordPress website with one of the leading CRMs, which is going to be ActiveCampaign. We're actually going to go through an actual example of how you link the two together to fire off a series of automated email using ActiveCampaign. And we're going to, during our series of webinars, we're going to be looking at a series of the leading tools and actively explaining the fundamentals and then giving you a practical example. Also, if you really want to support the show, go over to the WP-Tonic YouTube channel and subscribe. You'll be able to watch the bonus content of our interview with Matthew, the whole interview plus the bonus on the channel. So go over now to the YouTube channel and sign up. We'll see you next week with either another great interview or an internal discussion between me and Stephen. We'll see you soon, folks. Bye. So bonus content. So is it true that, like one of my questions, that most AI networks have about 300 neurons, but the human brain, I think some, what's it? I don't even know what the figure is. It's hundreds of billions, isn't it, of neurons?
Yeah, I had to look it up as well too. So yeah, the smallest neural network I'm aware of, which is called a perceptron, is essentially just two inputs, a neuron and an output. And that's essentially, you know, one neuron, 3 synapses conceptually. The largest that I'm currently aware of is something called GPT-3, which you guys may have heard of. It's making a lot of headlines right now. That has 175 billion parameters. And we can't think of parameters like neurons, but we can think of parameters like the synapses between the neurons. So there are definitely less than 175 billion neurons in this, probably a couple orders of magnitude. The human brain, the best estimates we have are that there's around 300 billion neurons and around 150 trillion synapses. So we're talking at least 100 times more synapses than, or parameters than the largest neural network we currently have today, which costs something like, I think it was over $5 million to train it, that model. And that's just the amount of compute to train it. And so we're talking at least 100x. The human brain's 100 times larger, which is 2 orders of magnitude roughly. And so most experts think we're going to reach parity where we'll have neural networks that are as powerful mathematically or computationally as what we assume the human brain has right now in around 2035 to 2050, depending upon who you ask. Some people think we'll never actually get there, and some people think it's actually going to happen even quicker. But if you took a random sampling of all the experts in the community, you'd end up somewhere between 2035 and about 2050.
All right, over to you, Stephen.
We brought up quantum computing a little bit. What's the difference between a neural network and quantum computing? Because I've read about both, and there's some similarities there, because it feels like you have this black box idea, no one knows what's going on, and there's this idea of training. But outside of that, are they just completely different? They shouldn't be thought about as the same, or there are even more similarities than just like those two aspects?
Yeah, they're mostly different, but they do have a bit of overlap. And the place that they overlap is that we're most likely going to be able to train neural network models with quantum computers at some point in time. And this is kind of where we get outside of my area of expertise. So if I'm making claims that are not true, I apologize. But it looks like we can use quantum computers to train the neural networks quicker than we could using traditional computers, and that will allow us to make more complex neural networks over time. But other than that, yeah, the only real kind of overlap is a purely kind of conceptual, this idea of a black box or the uncertainty principle in quantum theory or quantum mechanics versus the black box of a neural network model. But it's definitely 2 different types of uncertainty, though. One is at the base level of physics. Well, and once again, there's multiple interpretations of quantum mechanics, so it could be one of 2 different things. So I can't even say for sure which of those 2 types of uncertainty. But other than that, it's more of a conceptual distinction than like a real distinction. Fair
enough. If I'm trying to like explain neural networks to somebody that just barely understands computers at all, would it be fair to say that like a neural network is essentially like a decision tree that a computer controls, like where the humans don't make the decisions, the computer makes the decision and figures out what questions it needs to ask? Like, is that a fair way to like really dumb it down? I mean, I'm just far more complex than that. Or is that like completely ludicrous?
No, I see the analogy there. So when you think about a decision tree classifier in machine learning, which is literally a tree of decisions, given these inputs, then it asks the next level of questions based on the answers, then the next level of questions, and then the next, until you get down to either a yes or a no for a binary classifier.
And they're kind of also linked to the weighting, aren't they? This weighting thing, yeah.
So for each of those questions that we're asking, there's essentially a weight between it to the next question. And so if you think of every neuron as a question that then leads to another question, which leads to another question, another question, then metaphorically, they are, well, not even metaphorically, computationally, they are the same thing. We don't really think of a decision tree classifier for every pixel in an image, though. But I mean, in a way, it kind of is. And the way that you're kind of moving around in what's called a convolutional neural network is a bit different than just a simple decision tree. So the analogy does break down in certain ways, but the most basic understanding of it, yeah, there's definitely a parallel.
One question that was on here that we barely touched on was the whole idea of game theory. And you had said that, get back to that. And I'd just love to hear what your take is on like game theory and how that plays into the modern AI and those interplays there.
So interestingly, I studied game theory in college, but it was for economics, not for computer science. But the interesting thing is I do see concepts from game theory pop up in artificial intelligence literature all the time, especially in multi-agent artificial intelligence, where you've got cooperative, like swarms of AI working together, like drones building something together. So, concepts like, zero sum versus non-zero sum games show up all the time, cooperative versus non-cooperative games, perfect and imperfect information games all the time. And then, sequential versus simultaneous games, we have like pretty much exact mappings in machine learning for those types of processes that map to those types of games. And then like finite and infinite games. And then other things like Nash equilibrium show up all the time, evolutionarily stable strategies, decision theory. So they've really influenced one another. But that's the beauty of like scientific research. Like there's constant like feedback loops helping each other branch out. And even in like the neuroscience and computer science and data science space, like these things are all feeding back into one another, helping move the ball forward. And I think when we finally hit artificial general intelligence in another 20 to 50 years, it will be when the neuroscience meets up with the computer science and the data science, and that intersection is essentially artificial general intelligence.
So is neural network where is neural networks like the highest level of computing, like this concept, or do you think there are other concepts that are out there that we have yet to discover? Because at one point in time, neural networks we talked about it all, but like, is that the highest?
That is a really good question, and the best I can say is that throughout history, we've seen ebbs and flows in neural network being kind of the end all be all of essentially leading us to the holy grail of artificial general intelligence. There are some people that would say that it's the best thing we've got right now, and I would say as of right now, it is the best thing. But its known limitations mean that it will not lead us eventually to the artificial general intelligence. We will have to have something in addition to neural networks in order to finally get there. And there's a book called The Master Algorithm, I believe is the title of it, which if you're interested, I mean, this is the best explanation of it. They talk about the 5 different camps in AI space. And, you know, one of them is the neural network camp. We've got symbolic computation. We've got, I can't remember what the other ones are, and evolutionary algorithms. And they're talking about each contribution that they're making to get us towards artificial general intelligence and the limitations of each, showing why each one by itself will most likely not lead us to artificial general intelligence. But by combining these things or discovering something entirely new that we don't even know about yet will be necessary in order to get there.
Wow. It's so cool just to like to think about like everything adding up. Like you have your strengths and your weaknesses, you have all these different disciplines, and everybody is contributing to this idea of like, how can you make a computer that is smart enough to be able to make its own decisions in like very real and meaningful ways and keep evolving itself forward.
Well, and if you think about human intelligence as an example, it's clearly not just one of these solutions. I mean, you know, we have a neural network inside of us, but we have the ability to do symbolic and abstract reasoning. And this neural network was developed by evolutionary forces. So like you literally would have to think of combining multiple branches of computer science or AI science, if you will, in order to solve this problem of artificial general intelligence.
So are we doomed? Is eventually humans won't be needed and we'll just be all robots?
Well, there's, you know, if you think about the future of humanity and artificial intelligence, there's really one of 3 outcomes. Either human beings and artificial intelligence, well, let me state this. Either human beings get wiped out by AI or we accidentally wipe ourselves out. We work together forever, which is highly unlikely. Like, you know, if you look at the history of indigenous species or indigenous peoples versus a technologically superior force, it doesn't look good for us humans at some point in time. Or we learn to work with the machines and essentially merge to the extent that there's no distinction between artificial and organic intelligence. And I know it sounds really far-fetched, like the idea that we become like the Borg or something, but keep in mind, the Borg is essentially a character on television trying to, you know, incite fear in us about the dangers of technology. But like if you imagine human beings in technology synthesized in such a way that it's benefiting both of us, then that could actually be a pretty decent outcome for humanity. And I don't even know if you can call us humanity at that point in time, but that's pretty far down the road. And so I think the trick is we really need to be focusing on working together with the AI and improving our collective intelligence as both humans and machines, so that when we finally do get to the point that these machines are capable of being smarter than all human beings on the planet, like an artificial superintelligence, there will no longer even be an us versus them. Like it'll just be us. Like there is no humans versus technology. It's humans and technology are the same thing.
Right, as kind of to wrap up, funny enough that you touched this, because do you think at the present stage, not what you've just described, but at the present stage, actually, I think as doing my basic research for this interview, that a lot of confusion is caused by trying to compare present day artificial intelligence with human intelligence. That actually, I got the impression that causes confusion actually. And the reason why it happens is the one thing that artificial intelligence, you know, when you're dealing with specific problems that human intelligence isn't that good at, like consuming masses of data and seeing a coherent pattern in that data, most human intelligence isn't particularly good at that. But the main thing is speed. You know, artificial intelligence is so much the actual neural networks, the fundamentals. Is the calculations can be done at such a tremendous speed compared to what we think the human brain can calculate things, that it gives the impression sometimes of human intelligence, but they're extremely separate. Am I correct about that? There is a little bit, at the present moment, a bit of a problem that people think because the machine can mimic or seem to have what we call human intelligence, it's actually a really totally separate entity. I'm struggling for the right word, actually, Matthew.
I think there's probably 3 questions kind of hiding in there, and I'll just try touching on each of them. The first, I believe, is Edgar Dijkstra that said, asking if computers can think is equivalent to asking if a submarine can swim. And so the idea being that, you know, the conceptualization of human intelligence versus machine intelligence, they're vastly different. But what we're trying to do is get machines to perform tasks that human beings are currently doing, or tasks that human beings can't currently do. And when you think about the human brain and how it's evolved, it evolved in order to solve a very specific set of tasks. Things like face recognition, we're really good at it because you have to be able to recognize friend versus foe. Things like pattern recognition, if you can't detect the mouse versus the lion in a jungle, you don't survive very long. And we weren't trained or designed to do like complex mathematics. Like there just aren't very many situations in nature where your life or your death is dependent upon your ability to perform, linear algebra or multivariate calculus. So those things we just haven't evolved to be very good at. We've gotten better at them over the years, but it's not what our brains were designed to do. And so there's various pros and cons for human intelligence versus machine intelligence. And it's true that artificial neural networks are much faster in terms of their ability to perform the equivalent calculations. But like the human brain is significantly more energy efficient and dense. Like what we're packing computationally into this space is equivalent to what it would take like whole warehouses of computers right now to do. And it would cost millions of dollars in the electricity bill to do it, where we're doing it with like something like, 3 volts or 3 watts or something ridiculously efficient. And so the real strength of artificial intelligence, though, is automation. We want to allow machines to do what they do best, and we want to allow humans to do what they do best. And together, they're actually better when working together than either one alone. In fact, if you take a chess-playing computer and a human and you put them together, they're better than the best grandmaster on the planet right now. And they're better than the best chess program. This may have changed a couple years ago, but ultimately, combining humans and machines produces better results than either one on their own. And I think we'll see this especially in medical diagnostics. We're not going to replace doctors with an AI here anytime soon, but a doctor that uses an AI to help with his diagnostics and to act as a error checker, or, a fact checker for him is going to perform much better than a doctor alone or a machine alone. So the real strength of AI, at least from how I perceive it, is in collective intelligence, the intelligence of humans and machines together. One human is going to be able to do a lot more than even 10 humans without these machines, or 10 of these machines on their own.
Just the final question, it just occurred to me. So would you agree with this? I think in the present culture, the past five years with like, is it Boston Technology, whatever they're called, with these
Boston Robotics. Yep.
Robotics and this, and what we've seen with drones, this whole metaphor that we've had statements like from the former Stephen Hawkins and some other well-known public scientists about, now I think Elon Musk has made a statement around artificial, we're going to be wiped out by artificial intelligence if you're not careful. Do you think in some ways that it seems to me that there's always been a pattern here with technology, that technology has always been blamed for as a danger, but what I see it as, it's just a tool that focuses on the inequalities of the society of that time, that it just shows up that basically you've got a bad society model, and it's just easier to blame the new tool on the block that really shows up those inequalities even more. Do you think I'm on the right path there, or just talking nonsense, really?
No, I think you're absolutely on the right path. In fact, three thoughts occur to me. Number one, technology is a force multiplier. So if you've got a society of bad actors, you're going to essentially multiply the effects of those bad actors. Number two is technology is inherently amoral. It's neither good nor evil. We can use the same technology to either take mankind to the moon or to propel warheads into cities and kill people. So it's really up to us as a society to choose how we want to use these technologies, either for the benefit of all humanity or to essentially enslave people and make profit off of their suffering. And the third thought that I have with this is that, in times of crisis is where technology can either shine or be used for bad things. Like World War II is clearly the result of the industrialization or the mechanization of warfare. And we saw the negative outcomes of that. But the time period after that was some of the most progressive and amazing demonstrations of the positive uses of technology that we've ever had. And in the midst of a pandemic, a global pandemic right now, with an information pandemic as well too, and lots of stuff that most people on either side of the fence would clearly say are not good socially. This time of social unrest will likely be marked by a period of extremely positive technological progress after this. And we can kind of start to see it, like historically when we've had pandemics, the changes to society afterwards as a result have largely been positive and moved us forward. Like sanitation is a result of pandemics.
Yeah, it's funny that you just to finish off, because some people would say the period of the Black Death directly led to what's the word for the Renaissance period. There's some historical experts that say the Black Death period led to that because there was a shortage of workers because they're all dead, so people had to get more money, so they had more economical abilities, so that led to what you saw in Italy and that. So it's interesting. We could go on forever, actually. I have to come back sometime in the new year, Matthew. We're going to wrap it up now, folks. Hope you enjoyed this discussion. It's been a bit different. I've enjoyed it. Hopefully Stephen and Matthew enjoyed it. We'll be back next week with either a great guest or internal discussion between me and Stephen. We'll see you soon. Bye.